Okay, exactly. So that is it. That is what we were saying. And for the longitudinal strain, it was, we had 6. Okay, this is the value over here, and that is uh 6 times 10 exponent negative 4. I want to use this one, 6 times 10 exponent negative 4. Okay, that is 6 times 10 exponent negative 4. Okay, 6 times 10 exponent negative 4. At this point, 10 exponent negative 4 can cancel what? 10 exponent negative 4. So let's quickly do that, and then the rest is just an issue of mathematics. Better still, if you like, you can just punch it, tell us the answer, and we see how best we can proceed. So let's all do that together, and that is 1.8. 1.8 over what? 6. You realize that you are going to get what? 0.3. Okay, you're going to get 0.3. So that is it. So the 0.3 indicates that the material is a still. You see? So finally, our final answer is going to be what? Let's say we are going to get 3, okay, over 10, okay, which is going to be equal to 0.3. As simple as ABC. So we are done solving our first problem. That is problem 6.1. Problem 6.1. Okay, good. Let's also look at the second example. Okay, let's also look at the second example, and this is the second example. The problem says that determine the change in length, breadth, and thickness of a steel bar, which is 4 meter long, 30 wide, and 20 millimeter thick, and is subjected to an axial pull of 30 kilonewton in the direction of its length. Take elasticity to be 2 times 10 exponent 5 Newton per millimeter squared, and Poisson ratio to be 0.3. Okay, so we are just, the only thing we are supposed to determine over here is the what? Change in length, and also the breadth, and then the thickness of the bar. These are the members you are supposed to look for: the change in length, hot, the breadth, and then the thickness of the bar. These are the things that we don't know, we are supposed to look for. Okay. Okay, so that is it. Let's quickly see how we can put down our given and continue to what? Make history. So we are done with our problem 1. That is 6.1. We are now coming to problem 6.2. So let me quickly write that down. And this is what? Problem 6.2. Problem. This is my problem 6.2. Exactly. Exactly. So the first thing we are supposed to do is just put down our given. And this is our given. This is our given. Exactly. So let's quickly write down the given from the question. They say we should determine the change in length, breadth, and thickness of a steel rod. So first one, change in length. We don't know, so we put question mark. We are also supposed to look for the breadth. Okay, we don't know, so we just put question mark. Also, we are supposed to look for the thickness. We don't know, so we just have to put question mark over here. We were later told that the length is 4 meters. The length is the same as the L, which is 4 meters. 4 meters. 4 meters, you and I know that the 4 meters is also equal to what? 4,000 millimeters. Okay, so 4,000 millimeters. That is if you multiply it by 1,000. Because you know that 1 millimeter is equal to what? Or 1 meter is equal to 1,000 millimeters. Okay. So let's proceed. Let's proceed. And then the width of the bar is, let's say, 30 millimeter. Okay. Wide. Okay. And 20 thick. Okay. So let's say the bar is wide, okay, and we denote that as W, and that was given to us as 30 mm. Okay, okay, so 30 mm. So this question is actually telling us to calculate for the change in length, change in what breadth, and also the change in thickness. Okay, good. So in this case, we know that the width is also the same as the breadth. Okay, so what are we supposed to do? And then this is the thickness that has been given over here. So let's denote that well. So in this case, I can just rewrite this as what? Width or breadth, so that you get a clear difference. Okay, so this is the width. The width or the breadth is equal to B, let's say W or B. Don't get confused. It's the same thing, and we all know that it is equal to what? 30 mm. Okay, so let me put this over there, 30 millimeters. And now the thickness, the thickness is equal to 20 mm. Okay, just as you are seeing over there in the question. I'm sure we all have the question by now, and this is the thickness, 20 mm. So let's quickly put that down. So the thickness is the same as our T, which is equal to 20 millimeters. Okay, and is subjected to an axial pull of 30 kilonewton in the direction of the length. Okay, so load. This time it is a pull, you see. So the pull is the same as the load. So let me just write axial pull, and that is axial pull. So we say that our axial pull is equal to, and what is the value? The value is 30 kilonewton. So this is it, 30 kilonewton, 30 kilonewton. But we know that the 30 kilonewton is also the same as 30 times 10 exponent 3. 30 times 10 exponent 3 Newton. Okay. So as simple as that. As simple as that. Also, our elasticity that was given to us was what? 2 times 10 exponent what? 5. Okay, and the Poisson ratio is 0.3. So elasticity, let's put elasticity down. This is our elasticity. So our elasticity is the same as the E you are seeing over there. And it is equal to 2 times 10. Our elasticity is equal to the 2 times 10 exponent 5. Okay. So 2 times 10 exponent 5 Newton per millimeter squared. Finally, our Poisson ratio. Okay. So our Poisson's ratio was given to us as our Poisson's ratio. Finally, our Poisson's ratio was given to us. And we know that the Poisson's ratio is the same as this, but it was given to us as 0.3, telling that it is a still. Okay. 0.3. So from here, we can say that we are done putting down all the given. That is what we were given in the question. If you like, you can draw a diagram in addition to attract more marks. Okay. If you like, you can draw a diagram in addition to it to attract more mark. Okay. But if they say this is a pool, they say determine the change in length, breadth, and thickness of a steel bar, which is 4 meters long. And also, it has a weight of what? 30, and it's 20 mm thick, subjected to axial pulling. That you can just sketch something to also attract more marks. Okay, because of time, we just have to proceed. So this is solution. This is our solution. So this is our solution. Better still, if you wish for us to do that, then we can say that we can just draw a front elevation of that to assume the bar, and we can just put our load beside it. Okay. Yes, so that at least it can inform the examiner that we are aware of what we are doing. So this is the 30 kilonewton. 30 kilonewton. This is also our 30 kilonewton. Yes, so from here to here is the what? 4 meters. So from here to here is the 4 meters. Okay. From here to here is 4 meters, as we are saying. If you bring it in today's language, you say the 4,000. You understand me? So let's not waste my time on this diagram. Let's proceed. So this is our solution. Our solution of the problem. So this is our solution. Okay. So what are we supposed to know? First of all, we are supposed to calculate for the what? Area of the bar. But let's look at the things that we are being asked to calculate for. The change in length. If they say we should calculate for the change in length, we know that longitudinal strain is equal to change in length over what? Original length. We don't know any strain, so at the end of the day, you realize that we have to play with the formulas so that we can be able to get the right formula that will solve that. But first of all, let's calculate for the area. Okay. Since it is not a circular bar, if it was a circular bar, we'll be using pi d squared over 4. But since it's not a circular bar, I just have to multiply the breadth times the what? Thickness to get the area. Okay. Length times what? We have to multiply the breadth times the thickness. So first of all, we have to calculate for the area. And our area in this case, we are going to be using the formula, the breadth times the thickness. Okay. Good. We're going to be using the breadth times the thickness. So from here, we can say that our area is equal to the breadth that was given to us in the question was 30, and then the thickness too was 20. Okay. If you multiply these two, everyone quickly point this and let's see the answer you're going to get. So you see that this is going to give us what? 600 millimeter what? Squared, because they're all in millimeters. Okay. 600 millimeter squared. Don't forget, always remember to add the units. 600 millimeter squared. Okay. Good. After this, what are we supposed to do now? You are supposed to calculate for the stress in the bar. And we are just doing all of this because of what? We want to go and look for the what? The strain. Because we don't know the strain. We don't know this guy. So because of this guy, that is why we are doing all these calculations. Do you understand me? So from here, what are we supposed to do next? We are supposed to calculate for our stress. Okay. We are supposed to calculate for our stress because we know that I want to just highlight something to you. We know that what? This guy, longitudinal strain is equal to what? Change in length over original length. So to be able to get a change in length, you realize that we have to multiply the what? We have to multiply the longitudinal strain. Okay. We have to multiply the longitudinal strain by the what? The length. But the longitudinal strain, we don't know. For now, we don't know the longitudinal strain, but we know from somewhere that the longitudinal strain is equal to what? Stress over what? Elasticity. So why don't we calculate for stress, then we come and use this formula to calculate for the longitudinal strain, then we can use that to calculate for our change in length. It's just a smart move, okay? So that is what we are trying to do. That is why I'm calculating the area first to come and calculate for the stress. You see? Then I'll use the stress to go and calculate for it. So we are doing it step by step and gradually we will get there. Okay? Gradually we'll get there. Keep bringing your questions. You can send them to me personally. And then once I review them, I'm going to make more, or I'm going to make more points related to that to enhance your understanding. Thank you. So let's proceed to calculate for the stress as we wanted to do. So now let's calculate for the stress in the bar. I want to calculate for the stress in the bar. So we know that the stress is equal to force over what? Area. Okay. So the stress is equal to, or we can say load over the area. It's all the same thing. So the force over the area. Finally, this is what? It's just the P, which is the load, and this is the area, which we all know that it is calculated in Hot, but we can just denote here by A. So let's just, by substitution, let's substitute our values into the formula, and then we get the answer. Our load that was given to us was 30 kilonewton, and that is 30 times 10 exponent what? 3. Okay. The area we also calculate for, we had a 600 millimeter hot squared. So this guy is in Newton. Okay. So let's all quickly punch this together and see the answer we are going to get. That is 30. You can punch your division sign on the calculator and you punch 30 times 10 exponent what? 3. All over what? 600. Okay. If at this stage you are still finding problems with your calculator, then you are supposed to do well to see me in person so that I take you through the calculator extensively. Okay. Calculator is one of the things that can really limit you if you don't know how to use in this course, because you can really have an idea of what you are doing, but because you don't know how to use the calculator, it is actually going to curtail your development. Okay. Thank you. So we are all supposed to get 50 Newton per millimeter squared, 50 Newton per millimeter squared. Martha Okine had the answer correct, and that was very, very wonderful. Okay, so after we now know the value for our stress, it means that we can just calculate for our longitudinal strain. Now easy to go and find for the change in length. Okay, so from here we can say that our longitudinal strain. Okay, we can say that our longitudinal strain. We can say that our longitudinal strain. Okay, so let me write it this way. Our longitudinal strain now we can say it is equal to what? Stress over strain. Stress over elasticity. Stress over elasticity. So I'm denoting it over here. That is the stress over the what? Elasticity. Okay, good. Stress over elasticity. Better still, I could write it in full to enhance understanding. So this is what? The stress over elasticity. Stress over the elasticity. Stress over elasticity. From here, what are we supposed to know? We can just do substitution and then put our, but this over here can also be denoted as this is the symbols for them. So please don't get confused. Okay, good. Since our stress is known, our elasticity is known, we can just substitute it into this to get an answer. The elasticity given was what? 2 times 10 exponent what? 5. Okay. And then the stress, we had 50 Newton per millimeter squared. That is the 50 Newton per millimeter squared. This one to be had what? 50 Newton per millimeter squared. Okay. From here, what can we note? You realize that this is why we said that strain has no unit. This is going to take care of this. Okay. So finally, what conclusion can we draw? We can say that our longitudinal strain is equal to, everyone, let's quickly punch this into the calculator. Let's quickly punch this quick, and see the answer we can be able to get. And that is, after punching, you realize that you're going to get 2.5 times 10 exponent negative 4. That is 2.5 times 10 exponent negative 4. Okay. So this is going to be the answer for our longitudinal strain. Okay. This is going to be the answer for our longitudinal strain. So now that we know the longitudinal strain, it is clear that we can now calculate for the hot change in length. So we are now going to look for this guy over here. The one I've placed asterisk behind. We are now going to look for the change in length. Okay, as simple as ABC. As simple as ABC. As simple as ABC. At this point, I want to take some few questions before we proceed. Is anyone having any question, any difficulty, or any contribution he or she wishes to add to the study? Please, is anyone having any contribution he or she wishes to add to the study before we proceed? Okay, if there is no, then we can say that what? Finally, finally, comma, finally, we can now say that our longitudinal strain, okay, our longitudinal strain, finally, we can say that what? If, finally, comma, and that is we are saying that if what? If, listen, oh, if longitudinal strain is equal to what? Change in length over original length, then, comma, our change in length is equal to what? Longitudinal strain times the what? Original length. So finally, we can see that our change in length, we can use this formula to calculate for what? Our change in length. And it's as simple as ABC. So this is the formula we're going to use to calculate for our what? Change in length of the bar. So let's quickly proceed to do that. So I'm just going to write hash change in length and then history continues. So we are going to solve the change in length over here. So this is the change in length. This is the change in length. So I'm going to put this over here. So let's calculate for our change in length and let's proceed. Please, don't forget to type your don't forget to type your answers in the your questions in the comment sections. Okay, you can send them to me privately, or you can just type it generally. I'll review it and give you a feedback if you encounter any challenges or at any point in the video or the lecture. Thank you. So let's proceed. Also, don't forget to like, comment, and share my videos for more. And also, your challenges and your contribution are very, very much important, because these are the things that are going to help us to be able to develop the video for it to become the best version of itself. Exactly. So finally, we can say that the change in length can now be said to be equal to what? We know this one already. If I like, I can just still repeat the formula one more last time again before I do the substitution. As simple as that. So this is what we are saying. Okay. And finally, this is for the longitudinal strain. How did we get? We had 2.5 times 10 exponent negative 4. And that is 2.5 times 10 exponent negative 4 times 10 exponent negative 4. Okay. Times 4,000, because we know that the length was 4 meters. After your convention, you realize that it's going to be what? 4,000 millimeters. Okay. So 4,000 millimeters. If I add the units, you realize that after multiplying these two people, let's all do this together. 2.5 times 10 exponent negative 4. Okay. Yes. Times 4,000. And what are you going to get? You realize that we are going to get, everybody quickly partake in the calculation. Everyone quickly partake in the calculation. And at the end of the day, you realize that we are going to get 1.00. That is 1. We're just going to get 1 to be our answer. Okay. That is, the answer is 1 millimeters. Okay. Or if you see, or you can also choose to write it as 1.00. It is still the same thing. Don't get confused. Don't get confused. On this note, I continue to say that the laws of physics are the same for all observers in a uniform motion relative to one another. No matter how you apply them, once they are truth, they always speak the truth for themselves. Okay. So let's also solve for the other one. That is, we are supposed to look for the change in what? Breadth, right? So I'm putting hash over here. That is, we are now going to look for our change in breadth of the bar. Exactly. For the change in breadth of the bar, we know that we can use the lateral strain, the formula for the lateral strain, to get that, since we already know our Poisson's ratio. Okay. So we are saying that if, my statement starts with if what? If, comma, let's say our Poisson ratio, okay, is equal to a lateral strain. if our Poisson ratio is equal to the lateral strain over the longitudinal strain, if Poisson ratio is equal to lateral strain over the longitudinal strain, then we can say that, because if you do cross multiplication, you are going to make this guy the subject. Then you can say that then our lateral strain is equal to our Poisson ratio times the longitudinal strain. Okay. So our Poisson ratio times the longitudinal strain. And this is the longitudinal strain, LG. If you see LG, you know that is your longitudinal strain. Exactly. So by substitution, let's just do substitution and substitute our values and see the answers we are going to get. So we can say that our lateral strain, this, okay, is now equal to what? Better still, if you wish, I could use a different color pen to enhance your understanding. And finally, we can write that as this. That is our lateral strain. That is our lateral strain is equal to what? The Poisson ratio given to us in the question. Let's go back to the question. It was 0.3. You see, this is it over here. So it is actually 0.3 times the longitudinal strain. And for the longitudinal strain, what is the value we had? For the longitudinal strain, this is it, 2.5 times 10 exponent negative 4. Okay, so let's go and put it there. And that is 2.5 times 10 exponent negative 4. Okay, so good students should quickly punch this together with me, and let's see the answer we are going to get. Let's see the answer we are going to get. All right, so that is 0.3 times 2.5, okay, times 10 exponent negative 4. And you realize that we are going to get 7.5. Okay, what answer are we going to get? I want to check from the comment section to see if we are on the right path. Yes, someone got it right, and that was very, very, very wonderful. And that is what? 7.5 times 10 exponent negative 10, negative 5. Okay. It is a lateral strain. You realize that they all don't have unit. This guy doesn't have unit, this guy doesn't have, so it is unitless. Okay, so that is it. That is the answer for the lateral strain. Take note that we are not done. We are actually looking for the change in breadth too. So that even brought this formula. Okay. So now that we know the lateral strain, we can continue to say that since, listen on, since, then I put comma, or better still, I could just use a different color pen to make meaning or understanding more better. Yes, and that is since I put comma over here, and that is since our lateral strain, okay, since our lateral strain, since our lateral strain, since our lateral strain is equal to, let's say, change in breadth over the original breadth. Then in this case, because we are having breadth over, that's why I'm using this formula. Okay. So since then at the end of the day, we can just do some substitution and get our answer. Okay. So from here, whatever I've written over here theoretically can also be expressed as this. And that is our lateral strain. Okay, our lateral strain is equal to the change in breadth. Yes, all over the original breadth. Okay, so let's put the values into it. So the change in breadth of the bar is what? You don't know. You see that you don't know the change in breadth, and that is what we are going to look for. So if you do cross multiplication, this guy will multiply, this guy will multiply. You realize that our change in breadth, finally, our change in breadth, finally, our change in breadth is going to be equal to what? That is the lateral strain, okay, times the breadth of the bar. Okay, so if you do your substitution, if you do your substitution, you realize that you are going to get what? The lateral strain, what is the value we had? This is 7.5 times 10 exponent negative. So that is 7.5, okay, times 10 exponent negative 5. Okay, so all of this one is going to multiply what? The breadth. Okay, and what is the value for the breadth that was given to us in the question? The breadth was what? 30. You see, so we are just going to put a 30 into the question to solve the problem. So this is it, 30. Okay, so everyone, let's quickly punch this together and see the answer we are going to get. So finally, we can say that our change in breadth of the bar is equal to what? 7.5 times 10 exponent negative 5, okay, times 30. So if you multiply all these values, what are you going to get? You're actually going to get 2.25. 2.25 times 10 exponent negative 3. Anyone, let me check the comments. Yes. So I think some people are on the same side with me. Some people are on the same side with me. And that is, you're going to get 2.25, okay, times 10 exponent negative 3 times 10 exponent negative 3. Okay. So that is the answer for our change in breadth. Don't get confused. Whatever you are seeing over here can still be expressed in this form. Okay. If you see negative 3, it means that 3 zeros even came before all these values came. So this can be written as well. Look at, because this is 3, 0 point what? 0, 0. You see, before you can start bringing the rest, 2, 2, 5. As simple as that. As simple as that. Okay. So don't get confused at all. This, because this guy is in millimeters, the breadth was in millimeters, it will affect our answer to also be in millimeters. Okay. Yes, it's going to affect our answer to also be in millimeters. Okay. So it's left with the last thing we're supposed to calculate for, and that is the what? The thickness of the bar. Okay. Also, so you see that we are done with this one. We are done calculating for this. Okay. So let me write the hash thickness of the bar and let's wrap up for today's class. That is, here we are supposed to calculate for the thickness of the bar. Okay. So I will denote it as this. So this is the thickness of the bar. Okay. Yes, the change in thickness of the bar. So that is the other last thing we're coming to calculate for. Since we know that our lateral strain, okay, we know that the lateral strain, we know that the lateral strain, we know that the lateral strain is equal to what? Either change in what? Breadth over the breadth, or what? The change in, or the change in what? Change in diameter. Okay. Change in diameter over what? Original diameter. Okay. Or also, we can say that what? The change in, also we can say that all the change in thickness over what? Original what? Thickness. But in this case, since it is the change in thickness that we are interested in, we're going to pick this formula and maintain this one. Okay. So finally, we are saying that our lateral strain is equal to what? Change in what? Thickness over the what? Original what? Thickness. Okay. So from here, we are just going to do cross multiplication to get our what? Change in thickness of the bar. Okay. So from here, we can say that if you do cross multiplication, this guy is going to multiply this guy. So our change in T, or the change in thickness, is now going to be equal to, let's say, the lateral strain times the thickness of the bar itself. Okay. So finally, we are going to say that our change in thickness is equal to, for the lateral strain, we had 7.5 times 10 exponent negative 5. That is 7.5 times 10 exponent negative 5 times the thickness. And for the thickness, we know that the thickness that was given to us in the question over here was 20. Okay. So when we put a 20 over here, this is 20 millimeters. Quickly, let's all point this together. So finally, our change in thickness of the bar is going to be equal to 0.0015 millimeters. Okay. So this is the answer.